Hello and welcome to Thursday's edition of Cracking the Cryptic. I was just trying to work out what day it was then. And another puzzle by this incredible new setter on the world Sudoku scene. I say new, but Totally Normal Cat, or Totally Weird Caracal as I sometimes call him, has been around for a while. And, you know, the puzzles that this person is creating are quite extraordinary. Now this one is actually a couple of months old. It's called Unique, and it's a normal killer Sudoku apparently. I don't know why it's called Unique. I do know that it's 5 stars out of 5 for difficulty on Logic Masters Germany, so it's probably very hard indeed. But we're going to have a look at it in a moment. I have a couple of things to tell you about first. You may be wondering why the screen looks a little bit different. Well, this is because of my enormous computer problems, which literally I'm surprised I've still got hair. My desktop has given up the ghost, and I'm going to have to get a new PC. The order time on new PCs at the moment, as anyone who's looked into this will know, is not looking terribly favourable. I'm exploring all options and trying to get myself back on something that is not a laptop. But in the meantime, I am going to soldier on. I am going to keep cracking the cryptics, or cracking the Sudokus, and today's puzzle is an example of that. What do I need to tell you? Well, it's the first of the month, and that means if you're a patron of the channel, you get to play the sequel to Everything Is Wrogn by DiMono. Absolutely wonderful stuff. So get over there and try it out. Let us know in the comments how you get on and whether you enjoy the challenge. I'm sure that you will, even though the challenge is reasonably stiff. What else? Oh yeah, I've got exciting news as well. If you've been following the channel for literally years, you may be aware that I view the hardest puzzle I have ever seen of any kind, anywhere, to be a puzzle called Adventure. I did a video on this years ago. It's a puzzle that appeared in the Galactic Puzzle Hunt, and it's by John Snyder, and it took me a video just to explain the puzzle. Not to explain how to solve the puzzle, but what the puzzle's about. Incredible puzzle. Sort of starts as a text adventure and goes from there. Well, anyway, a friend of mine is actually trying to make the solution video for Adventure, and if he does manage to do it, it will be on the channel and it will blow your minds. So I'm very excited about this, and I'm hoping it's not too far away. With that said, let's have a look at this one. What do we have to do? It's normal killer Sudoku, so normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage, and digits cannot repeat within a cage, and apart from that, that's all there is. Do have a go. The way to play is to click the link under the video. Now I get to play. Let's get cracking and do battle once again with this caracal creature. So, unsurprisingly to me at least, I'm seeing no cages here that I can immediately write in the values. Even there's a few 6 cages dotted about. They've got 2 options. A few 15 cages dotted about. They have 2 options. I am seeing a lot of very high cages in box or touching box 3 here. So these squares add up to 34 plus 49. That's 83. Right, and this allows us to think about the secret. Because the secret, of course, is something I only tell my favourite people. These cells here, when we look at the finished grid for this puzzle, obviously these yellow cells will contain all the digits 1 to 9 once each. If you add up the digits 1 to 9, you get 45. So, if we know these cages here, the mouse is a bit slower than on my other computer, if they sum to 83, the minimum I could put into this square is obviously a 1, so that's 84. 84 minus 45 is 39. So these squares have to be 39 or more. Now, does that trigger anything in my brain? I don't think it does. 39 or more, so I could put 789 in there, that's 24. I couldn't put 789 here, but I could put I could put cells summing to 21. So I could have 21 and 24 is 45. So I think there are 6 degrees of freedom, or 5 degrees of freedom, depending on how you like to view the definition of degrees of freedom. Now, don't know. 27 in 4 cells does need to include a 9, because 8, 7, 6 and 5 only add to 26. I will note that actually, so there has to be a 9 in one of those squares. That's the first pencil marks of the puzzle, so that's good. Okay, not really seeing anything else. Oh, now hang on a moment. The other thing I've just noticed is this. That is a bit suspicious. So the arrangement of the 15 and the 6 cages, sort of in this corner, is, it looks like it's trying to create a box, doesn't it? A 5 by 5 box. And this is a pattern we've seen a few times. Sort of a pattern made famous by Ard van de Wetering from the Netherlands. Because this, if I highlight these cells, we can talk about it. So these purple regions here, actually the best way of explaining this is going to be to highlight this region as well. So I will do that. So if we look at rows 5 through 9 of the grid, we could define this purple region here as equal to 5 sets of the digits 1 to 9, because we know each row will have 1 set of the digits 1 to 9. So these bottom 5 rows contain 5 sets of the digits 1 to 9 minus the green region. But the last 4 columns of the grid are definitely equal, well, the purples up here are equal to 4 sets of the digits 1 to 9 minus that same green region. So the difference, the only difference between the cells in the bottom left and the cells in the top right is 1 complete set of the digits 1 to 9. Other than that, they contain the same digits. Now, yeah, you could take this a bit further. I'm not sure whether we are meant to do that here. Because what you can obviously do is then, once you know they've got the same digits other than a complete set of the digits 1 to 9, you could remove all of those from sort of both sets, if you like. And now we know that the purple, top right purple region is equal to the bottom left purple region minus 1 set of the digits 1 to 9. You can see we've got 7 cells there. We should have 16 here if I haven't gone completely mad, and we do. So that, what does that mean? Oh dear, I'm not sure. I'm not actually sure this is the right approach. There are quite a lot of gaps in this region. Sorry, yeah, I'm not sure. I think I might be misleading you. It's an interesting digression, but I don't actually know how to use that. Good grief, I'm not doing very well. So, what else can we say? Bottom left-hand side of the grid, I've also got lots of high digits in these cages, look. Double 20 plus 19 is 59. Ah, right, okay, we're off. 59. Now, if these squares add up to 59, and they do, what's the minimum I can put into those 2 squares? Well, that's going to be 1 and 2. So now I know that these squares together have a minimum value of 59 plus 3, which is 62. And that is a very interesting total. It's not quite enough, I don't think, for us to write anything in, but it does mean, because we know these are 45, therefore those squares have to be at least 62 minus 45, which is at least 17. So there must be a 9 in one of them and a minimum of an 8. Now the reason I'm pausing is that it is possible, I think, for that to be double 9, rather annoyingly. And if that's double 9, you could put 4 into those squares, i.e. 1 plus 3 into those squares. Bobbins. So there's definitely a 9 in here. There might be an 8, or it might be a double 9. These squares have to be, they have to include a 1, that is true. And they're either 1 and 2 or 1 and 3. So I'm seeing, the next thing I'm seeing is I've got whatever's in these squares affects the 15 cage that's sort of alongside them. Because, well, there's a virtual 8-9 pair in box 8 and there's a virtual 8-9 pair in box 4, because we know that the 15 cage must have an 8 or a 9 into it. And it goes with the 8 or the 9 there. So we've definitely got... So if these were different, then we would know these would be different. And if these are the same, then these are the same as well. Sorry about this. Let me just think about this. Does that matter? This is very suggestive, isn't it? These 6s and 15s. If they were all different, you know, if these 6s were different and if these 15s were different, you could write that square in. That is weird, because you couldn't put 3 into any of the cells then. That would have to be a 3, because it would see 1, 2, 4, 5, 6, 7, 8, 9. So maybe that's the game we have to play. Is there a way of proving that these, you know, these 6 combinations are different and these 15 combinations are different? I can do the 15s if I can prove these are 8 and 9. How can I do the 6s? Another 6 here. Ah, right, I can do the 6s. This is interesting. This and this cannot be different 6s. Because if they're different 6s, then this 8 cage would see 1, 2, 4 and 5 in these squares. And then how could we fill the 8 cage? There would be no way of doing it. It couldn't be 1, 7, it couldn't be 2, 6, and it couldn't be 3, 5. So these 6 cages must be the same. I'm going to colour them in. They are the same. And therefore that 6 cage, that must be different. So that's a different colour. Because obviously if this is 1, 5, you can't put 1 or 5 in this square. So this is different. So now, okay, well let's come back to the 15s then. If I can prove the 15s are different, we're cooking with gas. We at least get a digit in the grid. So I've got to prove that this is an 8-9 pair, which means I've got to prove this is a 1-2 pair, not a 1-3 pair. Three is much easier. If you think about these combinations here, if 3 is not in these yellow squares, you can put 3 in the 20 cage and you can put it in the 19 cage. If 2 is not in there, you can only put 2 in the 19 cage, because a 20 cage cannot have a 2 in it, because the other 2 digits would have to both be 9. So, is there a reason you can't put a 2 in that 19 cage? Yeah, there is. That is really clever. Good lord. Good grief. Right. We need to look at columns 1 and 2 now. 7, 8. That is really clever. Right. Totally normal cat being totally normal cat again. Look at the cages. Look at the big cages in columns 1 and 2. We've got a 19 cage here. Now, the interesting thing for me about a 19 cage is, can it be made up of digits that are not 8s and 9s? The answer is no, because 5, 6 and 7 only adds up to 18. So there must be an 8 or a 9 in that cage, or both. What about the 15 cage? Well, that needs an 8 or a 9 in it. A 20 cage must have an 8 or a 9 in it, if a 19 cage must have an 8 or a 9 in it, and the 19 cage down here. So we know each of these 4 cages must have at least one 8 or 9 in it. Well, let me ask you a facetious question, but I think it's quite important. How many 8s and 9s are there in column 1 of the grid in a correct solution to the puzzle? The answer is 2. There's going to be 1 8 and 1 9. How many are there in column 2? Again, the answer is 2. So in the 2 columns together, there are exactly 4 cells that need to contain 8s and 9s. Now, what would happen if any of these cages, therefore, contained an 8 and a 9? Well, there would be too many 8s and 9s in the column, because we know there's at least one in these 4 cages, and we know that there are exactly 4 in the 2 columns together. So if I was to try and put a 2 in here, then there would be an 8 and a 9 in this 19 cage, plus at least one there, that's 3, plus at least one there, that's 4, plus at least one there, that's 5. So that's a minimum of 5 8s and 9s in the 2 columns, and that breaks the puzzle. So you cannot put a 2 in this 19 cage. Therefore, the 2 must be joining its friend the 1 in the corners of that box, and we have liftoff, because now these 2 squares have to add up. I'm just checking the arithmetic. They do have to check. They have to add up to 17, and if they have to add up to 17, they must be 8 and 9. And now these 15s are different, and I am going to colour them in as well. That can be blue and that can be orange. And now this square has become a naked single, because it sees, between those 6 cages it sees 1, 2, 4 and 5. Between the 15 cages it sees 6, 7, 8, 9. This square is a 3. That means that an 8 cage now we've got a virtual 1, 2 pair in box 6, because the 8 cage now can't be 3, 5. So it's either 1, 7 or 2, 6, and whichever of those it is knocks the 1 and the 2, or the 1 or the 2, out of the 6 cage. Now, what does this mean? I do not know. There is something interesting though. Where do green and blue go in row 5 of the grid? These squares have to be green and blue. We don't know how they're disposed in those 4 squares, but because they are these squares... Oh, I forgot to put my phone on silent. That's going to be annoying. WhatsApp is one of the loudest things in Christendom. Now... Yeah, sorry, what was I thinking about? I was thinking about making these green and blue, because we know that purple is not green, and we know that orange is not blue. So in this row we've not managed to put greens and blues yet, and there are 4 green and blue squares. So actually we can do, yes, it's on green and blues. We can make those green and blues, and exactly the same way column 5, look, these squares they can't be green and blue, so they must be purple and orange. There we go. We've got a very beautiful grid. Now, what does that mean? That... I don't know what that means, actually. Not sure. Sorry. I'm tempted again to have another look at the... Oh, no, I know what I should do. I should colour in my 8s and 9s, shouldn't I? Because... Yes. I said before, these 3 squares contain an 8 and a 9. Well, whatever blue is, this square cannot be blue. So must be orange. And the same is true of this square. That's a blue square. Right, now where does orange go in box 7 of the grid? Now, we can't put orange in here, because if we do, we're breaking this rule we've discovered about columns 1 and 2, which is that there are only 4 cells that are 8s and 9s in the 2 columns. So if I was to have an 8 and a 9 in this 20 cage, I would reach a total of at least 5 cells in the column that have to be 8 and 9. So this orange can't repeat in its own cage, can't go in the other 20 cage, so it must be in the 19 cage in one of those little cells. So now orange is in one of these 3 squares in box 1. Blue. This puzzle is ridiculously clever. Now let's ask the same question about blue. Where does blue go? I'm not going to get a digit, but I do now know what this 20 cage is. Where does blue go in box 7? It doesn't go in its own box. There can't be a second blue in the 20 cage. There can't be a second 8 and 9 in the 19 cage. We've already looked at that. And if you put an 8-9 pair in there, you definitely need a 2, and that's going to break that as well. So blue goes in those squares. Now, if blue goes in those squares, this 20 cage now has an 8-9 pair in it. So those 2 squares add up to 17, and there must be a 3 in the cage, and the 3 must be here. So this is a 3 blue combination, which is not actually a combination I can show with colours, but it is still very interesting. Now blue... Yes, okay, and now ask, where does blue go in box 1? Box 1, it always makes, when I say box 1, it always makes me feel like I'm saying the word Botswana for some reason. No, where does blue go in box 1? Well, we know the 19 cage must have a blue or an orange in it, and it's not got orange, and the only square therefore that can be blue is that one, so that is blue. I think I will label that 8 or 9, if you don't mind, just so that I remember I'm talking about 8s and 9s, because the 15 cage, when I've coloured it in, it obviously caters for the 8 and the 9 and the 6 and the 7. So this is a 389 triple now. Let's put that in. Blue has to be in one of these 3 squares in box 9 by Sudoku, because we've not managed to put blue into those squares. When I say blue, I mean the 8 or the 9. The blue 8 or 9. Oh, bobbins. Okay, so more colouring required here, because look, the orange is also in those squares, so we can multicolour those. So there's now an 8-9 pair in these 3 squares, so we can maybe, oh, why has it done that? I want to put those in there. Those 3 squares have got to include 8s and 9s. I've got a magnificently colourful grid, but actually I've still only got 1 digit in it. Come on, Simon, what is it I'm meant to be spotting here? Oh, right. Here is something interesting. These squares, which are, remember, these squares are part of our 5x5 block in the bottom left-hand corner. Well, these squares sum to 45. They contain all of the digits. Now, the difference between the top 4, this 4x4 in the top right, and the bottom 5x5 was one set of the digits 1 to 9, which add up to 45. Now that's those squares in effect. So that means actually now we can say with certainty that this little bend of the Sudoku here, this bend and this bend are the same digits. Now, does that matter? I've now got 8s and 9s. These had to be highish though, didn't they? Can't remember what the maths was on that box now. I'll do it again. 34 and 49, 83. 1 here, 84. 39 is the minimum these squares add up to. Plus that, let's make that a 1 just for the sake of seeing what the absolute minimum the 7 cells add up to. So the minimum these 7 cells add up to is 40. Therefore the minimum these squares add up to is 40 because these are the same digits. Now we've got an 8-9 pair, and it is an 8-9 pair because they're different colours. So this is 17. So the minimum value of those 3 squares is 23 to get to 40. Oh, now here's an interesting point. Here is an interesting point. Can you repeat 8s and 9s in those 5 squares? No, you can't. These 2 squares, you can't put a blue in them because the blues are in there. And you can't put a blue in any of those because blue is already here, and the logic is exactly the same the other way around. These 2 squares cannot be an orange 8 or 9 because the orange 8 or 9 is in the 15 cage. So these squares need to add to 23 without including 8 and 9. Which is still easy, actually. Oh, especially as you could have double 7. You could have double 7, double 6, 5. Which is, unfortunately, 31. And that is more than the number we first thought of, which was 23. So I don't actually think I've done anything here by spotting this. This is very surprising, because that is a beautiful idea. So it's very redolent of what totally normal cat does. Sorry, I know I've clammed up here. I'm just thinking. Tick-tock, tick-tock. These digits are the same. So oh, I see. I see. Right. Right, well this is about the first example I think we've had on the channel of colouring with multicoloured squares being very helpful indeed. So, down here, I was thinking about double 7, double 6 and a 5. Now, if we did that, you'd have to go up here. We would have to put double 7s in, double 6s and 5s. So let's just think about 7s, right? Let's try and put 7s into these squares. 2 7s. Boom. There. That has broken the puzzle. That has broken the puzzle. Why has it broken the puzzle? That's the question. And it's absolutely beautiful. It really is absolutely beautiful, because you can see that if you go double 7 here, none of these squares here, none of, well, in effect, none of those squares can be a 7, because 7 is seeing all of those cells, either in this box or in this row. So none of those can be 7. Now what about blue and green? Can any of those be 7? Well, the answer is no, because we've got 7s there, seeing all those 3, and this 7 here sees that one. So, in fact, if you go double 7 here, it's not possible to put a 7 in anywhere in row 5 or column 5 of the grid, because you've ruled 7 out from all the colours. And that is going to be a problem. And that is a beautiful problem, because now we know we cannot repeat a digit. You can't repeat. Oh, you could repeat 3. Actually, that is a lie, what I just said. I didn't see that. You can repeat 3. If you put 3 into those 2 squares, 3, yes, you can, because now this square is the only square in effect that could be repeated here, because 3 is now not purple or orange, and it's not green or blue, but it could be this square. But 3 isn't the interesting digit, actually. That's fine, I think. The interesting digit is high digits. We now know that these 6 squares cannot include a repeated high digit at all. It's impossible. So the minimum I can make these squares add up to is 987654, which is 39. So the minimum these add up to is 39. And 39, the cages they're in 49, so that, hang on, let me just get this right. This, no, okay, hang on. The maximum these add up to is 39, because I can't repeat a digit. And if I substitute any digit other than 987, 65 and 4 in these 6 cells, I'm going to have a problem. Well, not a problem, but I'm going to be having a lower number than 39. So the maximum these are is 39. So the minimum these are is 49 minus 39. The minimum these are is 10. So this square is a 1. These have a minimum value of 10, because I can max these out at 39. We need 49 altogether in all of these squares. Now, 10 plus 17 is 44. Using the secret, which is that the box adds to 45, if I increase these to more than 10, this square would have to be a 0 or a negative number. Not possible. This is a 1. These do add to 10. Therefore, in fact, that's not a 9, therefore. Because if that was a 9, you'd have to put 1 here, which would clash. And these squares have to be the maximum they can be without a repeat, which is 987654. And we can't have a repeat, so the 9 being in here means there's no 9 in here. These 2 squares add to 10. I don't know, I don't really have a way of recording that. There's no 1 in this square anymore, which means there's no 7 in this square. This is as good a killer Sudoku as you will ever find. And we did that Glipperal one the other day, which was absolutely extraordinary. Now, what does this mean? I've now got a 1 here. I don't really see what that 1's doing. So I've got to do something else. This square is restricted because it sees, in fact that's a 1 or a 2, look. That sees all of those squares which are all different. So that this square sees a 4, 5, 6, 7, 8 and 9, it sees a 3, so that's a 1 or a 2. So that means we now have a very precise handle on what these squares are. These squares have to be 4, 5, 6, 7, 8 and 9 and either 1 or 2. What does that mean? Sorry, I'm not sure I understand exactly what that's doing. I'm sure it's doing something very profound though. If only I knew what it was. So this is very difficult actually. I'm now feeling almost lost. I've got some wonderful geometry in the grid, but I can't see what it means. I've got to put an 8 or a 9 in this 19 cage. Right, so the colour of the 8 or 9 in this 19 cage is blue because it sees this square can't be an orange 8 or 9 and these squares can't be orange 8 or 9. So there is a blue 8 or 9 in here which is not there. So there is a blue 8 or 9 in one of those squares. If we knew that blue was 9, we would know it was here because of the 9 there. I don't really want to. Should I pencil mark blues across this boundary? Will I understand what that means? I think I will do. I'm not sure. I'm not sure that's a good idea. Okay. What on earth do we do now? Am I meant to understand? I mean, this is clearly an enormous breakthrough. But I'm not sure I understand what it means beyond these squares having to be 4, 5, 6, 7. Well, 4, 5, 6, 7 and either 1 or 2 because the 8 and the 9 have been used up. 6. Oh. Ah, yeah, okay. Okay. So maybe it's the point is this. Whatever is the 4 and 5 digit in the purple, look, here. This 6 cage contains a 4 or a 5 and a 1 or a 2. Now, hang on. Yeah, my colouring is useful, I think, because this square is therefore not purple, because purple is here. So the 4 and 5 in here, if there's a 4 and 5, is not purple. But we know there is a purple 4 and 5 in this string of 6 digits altogether. So that must be there. And therefore those squares cannot be purple. So I think we remove purple from there. And purple 4 and 5 must be this square, I think. That feels logical to me. So I think that is a 4 or a 5. And that means this square is not this. So it must be the 1 or the 2. This is a 4 or a 5. That means what? I don't know. Down here, there has to be a purple 4 and 5. We now know that that can't be here. Well, actually, we know it can't be in any of those 3 squares, so it's in one of those 2. One of these 2 squares is a purple 4 or 5. But I don't really want to purple these in, because that's going to look like I've got 3 purple squares in the column, and it's all going to go crazy, because what I'm really saying is that there's a purple 4 and 5 together with this 1 or 2, which is also purple. Ah! Okay. What does that mean? Don't know. Sorry about this. I'm very, very confused. Oh! Hang on. If that's a purple... If that's a purple 1 or 2, that must be a green 1 or 2. So this square must be a 4 or a 5. And this must be a 1 or a 2. Oh, good grief. Right, okay. So now I've got, in this run of digits here, I've got a 4 or a 5, a purple 4 or 5, and a green 4 or 5. These squares cannot be 4 and 5, but we know that there's a 4 and a 5 in these 5 cells together. They must be there. I've got a 4-5 pair. I don't think I know what colour they are, but I do have them. And, right. Now, I've got a green 4-5 here and a green 4-5 here. So there must be a green 4 and 5 in this string of digits. So this string of digits doesn't only include a purple 4 and 5, it includes a green 4 and 5. And that means that means within this string of 3 cells are the digits 4 and 5. So they are not repeated in the 6 cells. So there is no 4 and 5 in these squares. And there is a 4 and a 5 in these squares. Oh, this is so clever. Right, now, let's come back to this cage now and do Sudoku on it, or killer Sudoku on it. There's a 4 and a 5 in it. That adds up to 9. That means the other 2 cells in it have to add up to 13, and they can't use a 4 or a 5, so they must be 6 and 7. So this square is a 6 or a 7. And there is no 8 in this cage. And if there's no 8 in the cage, the 8 must be here. Does that matter? There's an 8 in there now. This square now, we know those 2 squares together add to 10. So this is a 3 or a 4. I want to do central pencil marking, 3 or 4. 8, 9 is now here in this row. So this square, I was marking where the 8, 9 was in the 19 cage. It's not here anymore. That square can lose its colour, not its religion, and we can put 8, 9 in here. Now, oh, nearly, there's a blue in one of those 2 squares, look. Okay, all right. So what does that mean? I don't know is the answer. I'm not at all sure. These squares now, they've got to be 6, 7 and green. 6, 7 and green. There's a green in here, a green 1 or 2. This square is a 6 or a 7, but I don't I get the colour of that? Don't know. Good grief, I've got no idea what I'm doing here. 6, 7 here. So one of these squares aha. Right, okay. One of these 3 squares is a 6 or a 7. And whatever that is, look where it's going to go in box 8. It's going to go in the 15 cage because there's no 6s and 7s in these squares. So there's a 6 or a 7 here which goes in here. Which means, in effect, that this is blue. But it's the blue 6 or the blue 7. Actually, what I could do is I could have new colours, couldn't I? There's no reason I can't use 2 colours here. So now I'll make one of these black. So blue is the 8 or the 9. Black is the 6 or the 7 that goes with the blue in the 15 cage. So now, by Sudoku, one of these 2 squares is black. So one of these, it looks like this one, doesn't it? Sorry about this. I'm now getting very... So whatever... So I'm now going to, I think I'm going to have to do the same thing with the other 15 cage. I'm going to have to divide it in half, aren't I? So I'm going to use, maybe I'll use a lighter grey. Because, and the reason I'm thinking this would be sensible is that this square has to be the light grey 6 or 7. So I can put that one in. And that square must also appear in this run of squares, because it's not in these squares, which include 4 or 5 and black. So now, now I've got this one as possibly grey and this one as possibly grey. I think I'm going stark raving mad. And this run of cells now is 8 and 9. Oh, I could colour these in more. So this is 8 and 9, which are blue and orange. And look, I've got 3 colours now. This is a 3-colour triple. 8s, 9s, and whatever that is, light grey. So by Sudoku, on colours, I've got orange here and orange here, so I need to have orange in one of these 3 squares. That's not an orange 8 or 9. There's an orange 8 or 9 there. That's not 8. Whoa! Holy moly. We have logic. 8, 9 here. The orange 8, 9 up here goes with the orange 8, 9 here. Can't go there because that's orange 8 or 9. Can't go here. This is not light grey. This is just an orange 8 or a 9. And that surely is important, because now grey has to go there, and therefore that square is not black. This square is the only black square in... I get this digit. Oh, this is ridiculous, this puzzle. Totally normal, cat. Take a bow. Look at this. I've now got this square as black, which means this domino is exactly the same as this domino. This domino adds to 15. Those two squares add to 15. Therefore, this square is 4 by the power of maths. 4 sees... Oh, good grief, yes. 4 sees the 6 cage, which is now a 1-5 pair, which fixes the 8 cage now as not a 1-7 pair. That's 2-6. That fixes no 6 in here. So now we know that orange and grey, we know that 2 of these digits are appearing here, so they have to add to 15. That must be orange and grey now. So these are a 7-8 pair. This square is 5. This square is 4. This square is 2. Green is 2, not 1. And all of a sudden, I feel like I might be able to solve this puzzle. Why did I say that? Why? 7, 8, 9 here, so we can remove 7 from those squares now because we can't repeat a digit. So, oh, this is nice. So black is now 6, which goes here. And that must be a 9 to make 15. This is a 6-9 pair, which means this square is 8, which means those two squares are a 3-9 pair. We know blue is 9 now, so we can do that one. That means that's 8, of course. Grey must be 7. We've done the logic on that one. And this square is a 9 by Sudoku to complete box 5. Therefore, this square is known to be a 4. Now, 4 is green, so this is not blue. 9 is blue, so that's not green. These squares are 2 and 6. 2 is green. 6 is black, I think. So I need to get rid of the blue highlighting here and switch it for black. Is that right? I think that's right. And this square here must be a 3, which I've never coloured in. 3 is going to be the chromatically deficient colour. That must be 9. Light grey is 7. Yes, light grey is 7. Those two squares added up to 10, so that's a 3, which makes sense because the box adds to 24. I have to say that it does feel like whatever I'm doing here is, you know, it's not running into immediate mathematical issues. I need 2 and 6 into those squares now. So they are the same as this 8 cage. And those two squares have now got to be 1 and 3. I think I can get rid of the colour up there because we know these digits at the top are now 1, 7 and 8. Don't think we know the order yet. We know that's not 7. We know this isn't 1. If my computer fails now, I will weep. These have to add to 10, look. But I don't think we know very much about what's possible there. They have to add up to 11. Okay, so now I'm getting stuck. These squares here have got to be 1, 3 and 7. Now, what does that mean? Anything? This 1 sees the 1 and the 5 in this 6 cage. 1 is in one of those 3 squares in box 9. Do I know? Oh yeah, I know what that is. Look, that's got a 1 and a 2 looking at it. So 1 is not here. 1 is in the 13 cage along with 2 cells. Oh, yeah, okay. 1 is in the 13 cage along with 2 cells that must add up to 12, which are not 8 and 9, which must be 5 and 7 therefore. So this square can't be 1 or 5 and must be 7. This must be a 1-5 pair. That's not 7 anymore. Nearly. I feel like I've almost got something going along the bottom row, but not quite. 7 is not... Oh, 7 in this run can only go here now. So now we know those 2 squares have become an 8-9 pair, which means now 7 is grey. So this square now needs to be just grey. Let's just make it grey and remove the grey from those 2. Colouring has been an absolute revelation in this puzzle, hasn't it? It has absolutely helped me to solve it. 1, where does 1 go in box 1? Well, it won't ever go in a 19 cage, so it's in one of those 2 cells. Aha! And it's not in the 13 cage because 1 plus 3 is 4, which will make this a 9, which will clash. So that is not 1. 1 goes here, 1 goes here, 1 goes here, 3 goes here. So those 2 squares now have to add up to 12 without being 3, 9. So they are either 4, 8 or 5, 7, which means this square is 4 or 5, this square is 7 or 8. But I don't know if we know the colours. Okay. 7 or 8, so that could be... Oh, I know this is now grey or orange, but I don't think that's worth notating. Famous last words. So what are we missing here? What have we done wrong? Or wrogn? We have got to place... Whichever the 9 goes in of these 17 cages, it'll have to have a 2 and a 6 with it. Because 1 and 3 aren't available as other ways of getting to 8. Can we do any more in this column? I'm not immediately seeing anything. But it could be that I'm getting colourblind now. Those 2 squares have got to sum to 11 without being 2, 9 or 3, 8. So they are either 4, 7 or 5, 6. Not seeing how to do that. I'm not saying it's not possible, I'm just saying I can't see how to do it. This square's not a 1. Maybe get rid of the 1's pencil marked here. Sorry if you're all seeing how to progress this. I'm not being slow on purpose, I promise. In fact, this looks like it's going to be a 1 hour solve again, isn't it? Which is not surprising. This is brutal. Oh, 1. Look, that's not 1 anymore. So the 1 goes there. Oh, now I've got a 7, 8 pair here. Does that matter? I don't know. Don't know if it does or not. I can't immediately see why it might matter. So what are we missing? Gosh, imagine if I couldn't solve it now. That would just be absolutely horrific. 3 has to be in one of those squares by Sudoku. Twos, maybe? Oh, 2, yes, that's nice. Yes, 2s have to be in this domino. They're also in this domino. So now 2 has to go in here. Now, didn't that mean that we know... Yes, it does. The 2 will have to go with the 9, because we need, wherever the 9 goes, it needs 2 cells that add to 8 that can only be 2 and 6. So we now know this combination. In fact, we know where the 9 goes. The 9 must go here, which gives us the 2, and maybe this will crack it. 6 and 2 go into those squares. That square is now a 2 by Sudoku. The 6 is not there anymore. So these 3 squares now have got to be 4, 5 and 8. Which we might be able to do, but I can't immediately see how. There's definitely a 5 in one of those cells, which is not useful. 9 here is giving us the 9 and the 8 below it. That gives us a 9 in that row. The 8 gives us the 8 in this row as well. So this square becomes uncoloured, at least pro tem. 8 is orange, so we get rid of the blue from that one. We get rid of the orange from that one. We get rid of the blue from that one, and we get rid of the orange from that one as well. It's a bit of a shame to lose the multicolours at this point, though, I have to say. This 8 is seeing that square. That's become a 4 now. 4 is green. This square, there's no 4 in those there. So we get 5, 8 pair here, which is nice. That gives us a 4 at the bottom of the grid. And I will take every digit with a great deal of pleasure at the moment. Now, 3 looks to me like it's got to go here by the power of Sudoku. So that's not 3. Ah, yes. 3, 9, 9, 6. I know I can do some tidying up, but let's just keep going for the moment. 6 goes here, 6 goes here, which is lovely because I know there's an 8 in one of those squares. So I've got 14. I need a 5, 8 pair, which I can't do, but never mind. This is a 5, 8 pair. This square's therefore a 4. This is a 5. This square is a 1, that's a 7, that's a 3. That gives us the 1 and the 5 now. And these 2 squares have got to be a 4, 7 pair. Okay, nice, but still doesn't seem to crack the puzzle. The 6 gives us the 6 and the 2. Come on, crack! 6 and the 2. There's now got to be... Oh yes, there's got to be a 6 by Sudoku in this 19 cage. And therefore, there must also be a 4. And the 4 we can place. So the 4 goes here, the 6 goes here. That places 4 here. And places 6. And places 5. And that 5 and the 8 go in. Come on, keep going. This is a 2 or a 3 by Sudoku. It's not 3. There's a 3 in the column. 2s and 3s go in. This 4 is fixing this square as 5. Those had to add up to 12, so that's a 7. The 7 and the 8 go in. I still need to put an 8 in this column, so hopefully that's the 8. And hopefully that is a 3, which looks nice. Now, this 4 is giving me the 4, and the 7 and the 8, the 8 and the 5. Have I done it? I think I have. Shall I colour it in properly? Would people like me to do that? They probably would. So let's just do that quickly, if you don't mind, before I click check. 2 is green, so I need to get rid of orange into that square. Oh, this is a complete bugger's muddle up here. 5 was meant to be... I don't even know. 5 was meant to be purple, I think. 6 was meant to be black, so I need to turn that one black, that one black, that one black. Which means this one is not blue, this one is blue. This 3 needs to be uncoloured. 7s need to go grey. And the 2 and the 6 need to be resolved. We can remove that squares. There we go. 4s can be green as well as 2s. So all 2s and 4s need to turn green. Oh, that one needs to have its black removed. And Am I prepared yet to press the button? No, I'm not. I still want to do the colouring. 8s are orange, aren't they? 8s are orange. 5s were purple. 5s were purple. 1s were purple. 7s were grey. 6s were black. And only 3s at the end of this should be uncoloured. Let's double click the 3s. 1, 2, 3, 4, 5, 6, 7, 8, 9. The 5 there so I don't upset anyone. There you go. I think this is the solution. I'm now going to click tick with trepidation. Yes! That I am really proud of, actually. I know that's taken me an hour, but for once I don't think I was awfully slow on that. Let me know in the comments. Please let the video record properly, please. And thank you so much to Totally Normal Cat for another wonderful, wonderful puzzle. And see you next time on Cracking the Cryptic.